In this video, we are picking up with our topic on buffers. So just remember that we talked about what a buffer was. It resists a change in pH. That's its purpose. We went through some examples about what buffer systems will look at. We also talked about how buffers work and looked at how to calculate the pH of a buffer solution. So feel free to go back to that previous video if you want to review any of those topics. In this one, we're going to pick up with buffer capacity. So buffers do not have unlimited capacity. At some point, they are going to run out. So if we add a strong acid to a buffer, at a certain point, we'll use up all of that conjugate base that it reacts with until there's nothing left or there's an insignificant amount of it left. And at that point, you've reached your buffer capacity. And just keep in mind that the larger concentration that you have of your buffer solution, the greater the buffer capacity will be. And so a solution of 1 molar versus 0.1 molar, the 1 molar will have a greater buffer capacity. So when we're determining what makes a buffer suitable, one of the first components is that equal concentration, right? So we want to have about equal concentrations of the acid and its conjugate base. And if we get less than about 10% of one of those two, it's going to lose its usefulness. And so we tend to look at this as about a 1 to 10 ratio, right? So if we get greater than a 1 to 10 ratio, then that buffer has lost its usefulness. Now, weak acids and their salts are going to be more suitable for pHs that are less than 7, and weak bases and their salts are going to be more suitable for pHs that are greater than 7. And so when you look at a list of buffers, they are going to be unique to the pH range that they're suitable for. Okay, so some we've talked about in our own biological systems. We've got our stomachs; those are going to be very acidic. Our blood is slightly basic, and so a buffer that works in the range of our blood system in a slightly basic solution will not work in our stomachs in a very acidic solution. Okay, so you do have to match the buffer and the pH range that you're looking for. So when we start adding strong acids and strong bases to buffer solutions, we have got a shortcut that will avoid using the ice tables. And that is the Henderson-Hasselbalch equation. So this equation is great. It does help alleviate quite a bit of the math. And the pH in this case is equal to the pKa. So this all comes from your acid ionization constant Ka, right? And remember that little p means that we're taking the negative log of that Ka value. So pH is equal to the pKa plus the log of the concentrations of the conjugate base over the acid. Now, in order for this equation to work, there has got to be several factors that we need to check. Okay, so that's kind of the catch to this. The 5% rule must be valid. Okay, and we've got several other rules here. So if we want to use the Henderson-Hasselbalch equation, then we have to have weak acids and weak bases. And how we know that is we're looking at that Ka or the Kb value, and it needs to be less than 10 to the negative third. Now, in addition to this, we've also got to make sure that the concentrations of the acid and the conjugate base of the buffer system is greater than 0.01 molar. Okay, and this goes back to the definition of a buffer where you have to have appreciable amounts of each. And the ratio of the base to acid needs to be within that 1 to 10 ratio. Okay, so 3 things that we're going to check. Now, the Ka or Kb, it could be right at about the 10 to the negative third magnitude. That's okay. And we could have exactly 0.1 molar. That's okay. We just can't have greater than 10 to the negative third magnitude, or we can't have less than 0.01 molar. So let's see this Henderson-Hasselbalch equation in action. In the example here, what mass of ammonium chloride must be added to a 0.75 liter 0.1 molar solution of ammonia to give a buffer solution with a pH of 9.26, and they give us the Kb value. So in this type of question, we are preparing the buffer solution. So before we start using the Henderson-Hasselbalch equation for buffers, let's check some of those rules. So that Kb value that they give us, it is less than 10 to the negative third magnitude. So that checks off. And then we also need to look at the concentrations of the acid and its conjugate base. But the only concentration they give us is the 0.1 molar of the conjugate base, and that is greater than the 0.01. Okay, so that checks off as well. But the other two stipulations, which is the concentration of the acid as well as the ratio of acid to base, we can't check those off quite yet because we don't know what the concentration of the acid is. So that's our first step, is to figure out what is the concentration of the acid. And keeping in mind, just remember that the acid-base pair that we have here is the NH4, the ammonium ion, because that chloride ion is inert, and the NH3. Okay, and so of course ammonium represents your weak acid, HA, and ammonia represents the conjugate base, A negative. So the Henderson-Hasselbalch equation, we're going to go ahead and assume that we can use it, and we will double check to make sure that it's okay once we figure out that concentration of the acid. So pH equals the pKa plus the log of the concentration of the base over the concentration of the acid. And remember, we don't know the concentration of the acid, so that's probably what we're looking for in this equation. So the pH they give us, pH equals 9.26. They also give us the Ka value indirectly, right? They give us the Kb, so we can find the Ka, and then we can find the pKa. And then they also give us the concentration of the base, that 0.1 molar. So the only thing that we don't have is that weak acid concentration. So let's go ahead and find what the pKa is so we can plug all this in and solve for that weak acid. So the pKa, let's see, remember that Ka equals Kw divided by Kb. We know that Kw is 1.0 times 10 to the negative 14th, and Kb, which is given to us, is 1.8 times 10 to the negative 5th. Okay, pKa will be equal to the negative log of that value, the 1 divided by 1.8. So I'm just going to plug all of that in at once, take the negative log of the Kw divided by the Kb value. And if I do that, two significant figures means that I need to report at least 2 decimal places out. And pKa will be equal to 9.255. And remember, I keep that extra digit until the end. So now that I know the pKa, let's plug everything into the original Henderson-Hasselbalch equation. pH is equal to 9.26. Again, that's given in the problem. Equals the pKa of 9.255. We can see how important it is to keep that extra digit, because otherwise it would just be 9.26 on either side. And then we get the log of the concentration of the base, which is also given. That's that 0.1. Divided by the concentration of the acid, which we're trying to find. Okay, so subtract the 9.255 from the 9.26. When we do that, remember that for subtraction rules, the significance is only going to go out to the hundredths place, the second decimal place out. So whenever I get this value of 0.0047, right, technically the 4 and the 7, neither one of those are significant, but that's okay because we're keeping them for now. we know we at least have 2 decimal places out, and that value of 0.0047 equals the log of the 0.1 over our weak acid. And then, of course, to undo a log, we need to take the anti-log. And so we're going to take 10 raised to the power on both sides. And that removes the logarithm. And then 10 to the power of, remember when we're using these anti-logs, the number of decimal places that are significant, and so that's 2 decimal places out of significance, even though they're zeros, means that when I take 10 to that power, I'll get back 2 significant figures. Okay, so I'll get back 1.0 that are significant and then a 1. So 10 to the 0.0047 gives me 1.01. And then that is equal to whatever was buried in that logarithm. And so we have 0.1 divided by the weak acid. And of course, I can rearrange this to solve for the concentration of the weak acid. And get that that should be 0.00989. Okay, so I'm going to pick up on the next page. All I really need is that weak acid concentration, so I'll rewrite that down. And remember that overall we are looking for the mass of ammonium chloride. Okay, so in order to determine the mass, we're probably going to have to figure out the moles, and we're given the volume and the concentration of that weak acid. And so remember, that's the concentration of the ammonium ion. And so if I've got the concentration, it can be used as a conversion factor with the volume in liters. So 0.750 liters times the molarity of 0.0989 moles per 1 liter. Liters cancel, left with the moles, you get 0.0742 moles. And remember that however many moles you have of that ammonium ion, you have the same amount of moles of the original compound, that NH4Cl, because it's all a 1-to-1 ratio. And so if I've got the moles of the salt, then to find the mass, I simply use the molar mass. And so the last step is to take the 0.074 moles and multiply by the molar mass of ammonium chloride, which is 53.49 grams. Remember to use your periodic table to calculate that. And that is grams per mole. Okay, and 2 sig figs at the end to leave us with 4.0 grams. Okay, and just as a final note, we were supposed to check all of the things that give us the ability to use the Henderson-Hasselbalch. We did check the Ka or Kb being less than 10 to the negative third. The concentration of the base was greater than 0.01. The concentration of the acid was right at about 0.01, right? If we round all of that, it would become 0.01. So check that off. Plus the ratio was right at about a 1-to-1 ratio, right? 1.01. So the ratio worked out everything, and so we were able to use that Henderson-Hasselbalch equation. Okay, so now things get interesting. We're going to start adding strong acids or strong bases to the buffer solution. So in the first step, we need to calculate what is the pH of the solution before we add a strong acid or a strong base to it. And so when we do that, again, let's check all of our rules really quick. So 1.8 times 10 to the negative fifth, that is less than 10 to the negative third. so that checks off. 0.2 molar and 0.6 molar, certainly greater than the 0.01 that we need. And the ratio of the two, so if I take 0.6 divided by 0.2, I get a ratio of about 1 to 3. Okay, which is well within that 1 to 10 ratio range. So everything checks off. Looks like I can use the Henderson-Hasselbalch equation. They give me the Ka value, and so I can basically plug everything in. Right, so the pH equals the pKa, so that's going to be the negative log of our Ka value, 1.8 times 10 to the negative fifth. And then add that to the log of the concentration of the base. So we always look for that base first. Now this is acetic acid, so of course that is going to represent our HA. And so sodium acetate, if we remove that inert sodium ion, we get acetate, which is the A negative. That's our base. So the concentration of the base must be the 0.6 divided by the concentration of the acid, that's the 0.2. Okay, now we will solve for each logarithm individually just to check for sig figs. So the first logarithm, we've got 3 significant figures, that's 3 decimal places out, so we get 4.7, 4, and then the 7 is not significant, that's the 3 decimal places. Add that to 0.4771. Again, 3 sig figs, so 3 decimal places. And that will be a pH, 3 decimal places out, of 5.222. Okay, so that Henderson-Hasselbalch equation saves us a lot of time from using the ice table. Now, let's try this again, but instead we are going to add a strong acid to that buffer solution. So here's where things can get a little tricky. A buffer solution is prepared from equal volumes of a 0.2 molar acetic acid and 0.6 molar sodium acetate solution. Use the 1.8 times 10 to the negative fifth for our Ka value. What is the pH? And remember, pH, we're always looking for that hydronium ion concentration at equilibrium. That's what matters to us. What is the pH of a solution that results when 3 milliliters of a 0.034 molar hydrochloric is added to the 0.2 liters of the original buffer? So what is tricky here compared to all the previous examples is that the volume is changing. Right now we're adding 3 milliliters to essentially 200 milliliters or 0.2 liters of the solution. And when the buffer solution was created, we had equal volumes of each. Right, so to get that 0.2 liters, that means that we used 0.1 liter, half of that, of the acetic acid, so the 0.200 molar, and acetic acid, we're going to mark that out and write it as HA, generalize it. The sodium acetate, we're going to mark that out and write it as A negative. So we used 100 milliliters or 0.1 liters of a 0.2 molar acetic acid solution, HA, that's our weak acid. We also used 0.100 liters of the 0.6 molar weak base, the sodium acetate, to give us an overall solution of 0.2 liters. Right, so those two added together would give us the 0.2. Okay, so what that means is that if the volumes are constantly changing, then our first step is to convert everything into moles. So we are first going to have to figure out how many moles that we have of each compound, and then we've got to react that with the hydrochloric acid. And so we're going to use what's called a BCA table. You may have seen this in General Chemistry 1. If not, you might want to go back and review. It's very similar to an ice table, except that this is what we use for reactions. The B stands for before, C for change, and A for after. So this is where we have limiting reactants, and everything in a BCA table typically is in moles. So let's first take everything that we've got and convert it into moles. And when we've got liters and molarity, we can simply multiply those together to get the moles of each compound. So let's start with the 0.100 liters times the 0.2 moles per liter of our weak acid. And so we've got 0.02 moles of the weak acid. Okay, do the same thing for the base. And that will give us the 0.06. And then we can't forget that we've also got to do it for the strong acid that's being added. And as 3 milliliters, we have to convert it to liters before we can use it. So 3 milliliters, make sure to divide that by 1,000. And so that will be equal to 0.003 liters times the concentration of that acid of the 0.034 moles per liter. And that is equal to 1.02 times 10 to the negative fourth moles and of HCl, which remember is the strong acid. So whenever we have strong acids, they go to full completion, which means the moles of that strong acid is equal to the moles of the hydronium ion, right? So we have the moles of the hydronium ion, and that is going to react completely with our weak base. And so we're going to create a BCA table, which is very similar but different to that ice table. And so in this table, we're still going to start out with the weak acid. And technically the arrow for a BCA table, it's going to go all in one direction. So we might want to rewrite this. I'm going to rewrite this so that we have the hydronium ion reacting with that conjugate base. So that conjugate base will react with the hydronium ion to completion to give you the concentration remaining of the weak acid. And we'll have before, change, and after. Okay, so the original concentrations of each, not concentrations, we want to use moles. We have the moles of the weak base, that's the 0.06. So 0.06 moles of the weak base. Weak acid, we calculated that as well. That's the 0.02 moles. And I'll even write over here, all of this is in moles. And just remember, B stands for before, C for change, and A for after. So this is a reaction that's going to completion. And then the hydronium ion, moles of the hydronium ion was equal to the moles of hydrochloric, and that is 1.02 times 10 to the negative fourth. Okay, so when we're deciding how much to subtract and we're looking at our two reactants, as long as it's a 1-to-1 ratio, it's whichever one is smaller. And so, of course, the hydronium ion concentration is smaller, and so that is what we call our limiting reactant. Right, and so as our limiting reactant, we are going to use up all of that hydronium ion until there's nothing left. And so we're going to react the same amount. The change for the weak base will also be 1.02 times 10 to the negative fourth. And then if we are removing that from the reactant side, we're going to add that amount of change to the product side. And so 1.02 times 10 to the negative fourth. Okay, so you can see very similar to an ice table. The big differences here are that we are using moles instead of concentrations. We are determining the limiting reactant, and once we determine that, we use it all up, and that becomes the change for the reactant and the product side, right? The reactant side will be negative change, and the product side will be positive. And so your limiting reactant should come to 0 at the end. And so we subtract that amount of change from the weak base, and you'll get 0.0201. And same thing for the acid, we add that to it. Oh, oops, I'm sorry. This becomes, sorry, we subtract it, we get 0.0599. And then we add it to the weak acid, that gives us the 0.0201. Okay, so now we have our moles of weak acid and moles of weak base. And remember, with the Henderson-Hasselbalch equation, we got that pH equals the negative log. Oh, sorry, pH equals pKa plus the log of the weak base over the acid. And those are in concentrations. So we're very close to being able to use the Henderson-Hasselbalch equation. The only issue is that we have both of those in moles, and we need to get it into concentration values. To do that, we've got to take the moles and divide it by the total volume in liters. And remember that you had a 0.2 liter buffer solution, and you added 3 milliliters of hydrochloric acid. So the total volume of the ending solution is going to be 0.203, 203 milliliters, or 0.203 liters. So we'll take each one of those moles of the conjugate acid and its weak conjugate base and divide by the volume to get the concentration. Okay, so moles divided by liters, and we get 0.295 molarity, and that is for the conjugate base. So that is the molarity of A negative. And we'll do the same thing for the weak acid. You've got the 0.0201 moles divided by the 0.203 liters. And that will give us 0.0990 molarity of the weak acid. All right, let me see if I've got another. Nope, no more space here. So I'm going to erase and rewrite this Henderson-Hasselbalch equation, but fill in all of the values that we know. Okay, so the pH, which is what we're looking for, is equal to the pKa. And remember, we already calculated the pKa in a past example. It's the negative log of that 1.8 times 10 to the negative fifth. We did that back in part A. Right, negative log of 10 to the negative fifth is equal to 4.7447. So pH is equal to that 4.7447 pKa plus the log of our the weak base. So that's in concentration as 0.2951 divided by the concentration of the weak acid. That's your 0.09901. Okay, plug all of that in. You'll find that you'll go out to 3 decimal places for both of those values. And so the pH becomes 5.219. Okay, and let's just look real quick. Buffers, the whole point is to resist a change in pH. Had we added that 0.034 molar hydrochloric to that solution, it would have dropped that pH because we would have added pure hydronium ion to water if it was unbuffered. But because of the buffer, because of that hydronium ion reacting with the conjugate base, our pH only went originally from 5.222 down to 5.219. All right, so you're talking about 1,000th of a place of a pH. So most pH meters wouldn't even recognize that change. So that is how a buffer will resist the change in pH from a strong acid. Okay, and we'll do one last example here where we have got a strong base that is being added to the buffer. Okay, so in this example, calculate the pH after 1 milliliter of a 0.1 molar sodium hydroxide is added to 100 milliliters of an acetate buffer that is a mixture of 0.1 molar of each the acetic acid and the sodium acetate, and of course use that same Ka value that we've been using. So just as a refresher, remember that when we are adding strong acid or strong base, that we have a reaction that's happening. We're going to have to use a BCA table, and so we're going to have to find the moles of each because the volumes are changing. This time, the buffer is 100 milliliters of a 0.1 of each, and so we don't have to do that kind of divided by 2. And just to review the difference in the wording here. In the first example, we had a buffer solution is prepared from equal volumes of a 0.2 and a 0.6. And so here we had those two solutions separate and we added them together to get that total of the 0.2 liters. But in this example, we don't have to do that because they are telling us that we have 100 milliliters of a pre-mixed solution that is 0.1 acetic acid and 0.1 sodium acetate. So no need to figure out the math on that. We can simply use the 100 milliliters of the 0.1 of each. So milliliters in terms of liters, of course that's going to be 0.1 liter times the 0.1 molar. And that will give us 0.01. And that is moles of the weak acid. So acetic acid, we'll relabel it as HA. And then sodium acetate, of course, the sodium is inert. The acetate is our conjugate base to acetic acid. And so this is moles of the weak acid, but it's also the moles of the weak base because both have the same concentration of 0.1 and 0.1. Okay, so that's also equal to the moles of the weak base. And then the last one is the moles of the strong base that's being added. So you've got 1 milliliter. So of course that's 0.001 liters times the concentration of sodium hydroxide, which is 0.1. And so that's 4 decimal places out, 0.00010, or 1.0 times 10 to the negative fourth moles of sodium hydroxide. Of course, this is a strong base. It's going to fully dissociate, and so moles of sodium hydroxide is equal to the same thing as moles of the hydroxide ion. Okay, we've got moles of everything. Let's go ahead and create that BCA table. Now this time, because we have the hydroxide ion, that is going to react with the weak acid. And so this time we'll have the weak acid on the reactant side plus that hydroxide ion, and then that is going to react fully to form the weak base. And we have, of course, water hanging out here on the product side, but we don't care about that because it's a liquid, so we don't need it. Looking at that BCA table, and the initial, and remember all of these are in moles, so the initial amount in moles of that weak acid is the 0.01. And same for the moles of the weak base, right? That one's also the 0.01. And then the hydroxide ions that we're adding, that is the 0.0001, or 1 times 10 to the negative fourth. And we need to figure out our limiting reactant, and of course that is going to be the hydroxide ions. You can pretty much assume for this class that the limiting reactant will always be either the hydroxide or the hydronium ions. So we're going to use all of that up. That's our limiting reactant, and so that becomes the change for everything, right? Negative changes on the reactant side, so negative, and positive on the product side. And then in terms of decimal places out, your weak acid, weak base will limit it to 4 decimal places out. And so we get, let's see, 0.0099. And for the weak base, we get 0.0101. So all of those are significant. And then, of course, the hydroxide drops down to 0. Okay, so we don't care about that. But what that does give us is it gives us the moles of our weak acid and our weak base in this buffer solution so that we can use it in the Henderson-Hasselbalch equation. So what we care about are those two values that we got in the after, but of course those are in moles, so we've got to figure out what they are in concentration. And so we need to divide by the total volume. And the total volume is, we've got 100 milliliters of the buffer solution, and we added a milliliter of the sodium hydroxide. So total volume there will be equal to 101 milliliters. Okay. And we're going to assume that 100 milliliters has a decimal, and so we'll treat that as having 3 significant figures. Okay, so for the concentration of the weak acid, that will be equal to the moles of the weak acid, 0.0099, divided by the total volume of the solution of 0.101 liters. So of course I converted those milliliters into liters. Concentration of the weak acid will be equal to 0.10, and I had to add that 0 back on, right, because of 2 significant figures. I still need 2 significant figures. oh, oops, I'm sorry. I wrote that incorrectly. The concentration of your weak acid is, 0.098 molar. The concentration of the weak base will be the 0.1. So that's equal to 0.0101 divided by the 0.101 moles over the total volume in liters. And so concentration of that base is equal to 0.1 molar. Okay, so those are the values we care about. We got that concentration of the weak acid. We've got that concentration of the weak base. And so I'm going to rewrite those down so I have a fresh sheet. Okay, and last step is to use that Henderson-Hasselbalch equation. So you can tell these problems do have quite a bit to them. And a lot to keep up with. So you do have to practice and get into this pattern of all the different steps that we have. So Henderson-Hasselbalch equation, pH equals the pKa, and we've seen this several times. That's that 4.7447. Again, I'm just taking the negative log of that Ka value, and plus the log of the concentration of the base over the acid. So that's 0.10 over 0.098. And those only go out 2 decimal places. Or sorry, the log of that, those numbers are 2 significant figures, and so the log of it will only go out 2 decimal places. So we get the 47447 plus the log will be equal to 0.0088. So remember, only goes out 2 decimal places because of the 2 significant figures there. And we want to keep the 8s until we're done so that we can see the pH changes, and gives us 4.75 out to 2 decimal places. Right, so we saw a very slight change from 4.74 to 4.75. Okay, and that ends our topic on buffers. The last video series for acid-base equilibria will be the acid-base titrations.